alcohols can be made from epoxides. And alcohols, from here on out, should be thought of as being made from epoxides. Now you have other alcohol synthesis methods, such as hydroboration, to give an anti-Markovnikov alcohol, or oxymercuration, demercuration, to give a Markovnikov alcohol. The thing about epoxides when you react them with a Grignard, is you do two things. Not only do you generate an alcohol, and if you have a chiral epoxide that's optically active, your alcohol is also, if it's chiral, it's also optically active. But you also make a carbon-carbon bond. In this case, I made too many carbons. Like so. The above reactions here they make an H and OH bond, but they do not make a carbon-carbon bond. But here, in addition to making the alcohol, you make a carbon-carbon bond. Something to keep in mind. The hard part is disconnecting, going from working backwards from the alcohol given back to the epoxide and the Grignard reagent. Now, thing to remember is the bond that's made. There's you have the alpha carbon, beta carbon, gamma carbon. The hard part is remembering which bond is made. When you work with epoxides, you make the beta-gamma bond here. Or in this case, we have actually two beta-gamma ones. And in order to figure out which one you ultimately have to use, you have to work backwards on both. And to figure out which epoxide, specifically which diastereomer of epoxide you start with, you have to redraw the molecule and remember that your nucleophile and the OH end up anti to each other. Important. So, let's take a look at, first of all, if we make this beta gamma bond here. So I'm going to redraw this alcohol so the OH is a line. That puts this propyl group here as a wedge. And this propyl group here, thankfully, is already a line. So this OH and this propyl group are anti to each other. This methyl group is here. Now, to plan this out, what epoxide is used, we're going to do an example of a bad mechanism. Think of it as a reverse reaction of a nucleophile opening up the epoxide. We're going to go backwards and have the alcohol come down, form a three-membered ring. That pushes the methyl group down and kicks this off. This, of course, in order to get an optically active product, you have to have an optically active starting material. Like so. And this part becomes your Grignard. Again, it's very useful to number carbons. Of course, this is carbon 9. I'm still attached to 9. To make sure that you don't inadvertently add a carbon. And so, to actually make this alcohol right here, you would simply a Grignard plus the epoxide is actually a two-step reaction. The first step is done in ether. The second step is the H3O plus step, and then you draw your epoxide. Like so. And that's optically active. And your Grignard. If you have to make your Grignard reagent, which you'll inevitably have to do because Grignards are pseudo-ionic compounds, very unstable, so you have to make them typically the day that you use them. Make it from the bromide plus magnesium. Yeah. So this is a perfectly straightforward synthesis. Now, keep in mind, we actually had two gamma carbons. So if we chose to make this one right here, we would need to redraw this molecule. So the methyl group is our nucleophile. So the OH comes a line. Propyl group over here is a wedge. And we need to redraw it so the nucleophile here, the methyl group is here. And then the methyl goes to where that propyl group is. So this propyl group becomes a dash. Like so. If we use our cartoon space, there kicks the methyl group off. This is our epoxide, and this molecule is chiral, so it can be optically active. And react it with our methyl anion, so this becomes our Grignard reagent. So on the forward sequence, methyl magnesium bromide plus the epoxide. It's optically active. First step's done in ether. Second step, H3O plus, will give us our product, which is also optically active. There is actually another gamma carbon that can be added to make this alcohol. That's the alpha carbon. This over here can be the beta carbon, and this can be the gamma carbon. And so you could actually make this bond right here as well. So to make this alcohol, there's actually 3 equivalent routes. Each of them goes through an optically active epoxide in order to give an optically active product.